Okay, can everyone see the slide? Woo! Okay, so today I'll be talking about this reasonably small natural product called Loline, and I thought this is a good starting point to start learning some retrosynthesis concepts because it's not it's not gonna be a 30-step synthesis where halfway through you forgot what you started with, right? They're short enough, so it's easy enough to hold everything in your mind. So Lolines, honestly, I don't give a crap about their biological activity because it's like insecticide stuff. So it's produced by a fungus that like lives inside the plant, and it starts with what? This is amino acid proline and some non-normal amino acid. I thought, yeah, here's Loline in this whole sequence. There's this one really badass step catalyzed by the enzyme LOLO, where it just says, I want the oxygen atom right here, and just slams it in there. So that's a pretty impressive oxidase right there. But anyway, why do we care about this molecule? Because we're organic chemists, and we just want to show biologists that we can make the molecules. So the goal of retrosynthesis is to rapidly simplify the structure in a way that is feasible, like there's a reaction that can actually do it, and strategically advantageous, like it's a good move, like in a game, right? Okay. So let's talk about some shit moves, right? So let's consider breaking this bond between C1 and C8. Now, if you break this open, this 6-ring and 5-ring system is still there, and it's still a pretty complicated system. So it's not strategic, right? And then if you actually think about trying to break this, no one knows of any bonds that breaks a CC bond between two amines like this. I mean, maybe it exists out there, but I don't know of any, and it's not that common. So this is not tactical, nor is it strategic. An example of a bond that is tactically possible is this bond between nitrogen 4 and carbon 5. So if you cut this, everyone knows you can do SN2, you can do reductive amination to break these kind of CN bonds. But the problem is this ring system, this 5-5 system, I think that's what it is. Maybe I'm wrong. Maybe I'm wrong with the naming, but who cares? The point is this system is still complicated. Okay. And one more bad disconnection is this carbon 2, carbon 3 bond. So if you imagine breaking this bond, it's strategic because now you have a much easier system where the 5 and 5 are fused with just no carbons between them. So it's not a bridged system anymore. So it's just a simple bicycle. But the problem is, how are you going to break this bond, right? This is a bond between the carbon of an alcohol and the carbon of an amine. Again, maybe it exists, but I'm not familiar with any, and it's not like part of what everyone knows about, right? So this is kind of like the struggle that you have with retrosynthesis, because you'll look at a complex molecule and you're like, what the fuck? Like, what bond do I start with? Because there's so many bonds, and every bond you break has so many other like branching trees. But then the good news is you just gotta pick the easiest bond and you just start working from there, and you'll see things evolve outwards. So here are some examples of bond disconnections that were used in the syntheses I'll cover. So everyone knows that you can make carbon-oxygen bonds with SN2. And so if you cut either this CO bond here or this CO bond here, let me try my laser pointer. Okay. Then you'll find that you'll simplify yourself to a 5-5 bicycle. Either way, right? Whether you cut this bond or this bond. And there's no bridging, as in there's no carbons in between where the two rings are fused. So this greatly simplifies the structure, and it's possible to, there's like a chemical reaction that can be associated with that, right? The last transformation that was also covered is this CN bond breaking. So now you have this bicycle, this 5 and this 5. So this is also used. So this is kind of an example of the kind of starting points that people might begin with when considering how they want to break apart their molecule, right? Okay. So the last thing is special moves, right? So these are like your combos. So combos can be really powerful because they're called cascades, I guess, because you can make multiple CC bonds in one reaction, and you can put your other heteroatoms, like your oxygens and your nitrogens, where you need them to be. I mean, there weren't any discovered for the scaffold, but whenever you're doing any kind of retrosynthesis, it's always good to take a step back and ask if you can see any cascades that could occur. Okay, great. So we're going to talk about the first synthesis first by the Tufariello group. I don't know how it's pronounced. They did a racemic synthesis of Loline. And so you see that they started with the disconnection that we had earlier discussed. And so you can see that I inverted the stereocenter, right? Because there was SN2 occurring at it. And so if we take this and just unfold it, like smushing it flat against the page, then you would probably agree with me that I had the stereocenters drawn here correctly. And just to note that this leaving group, we usually think of leaving groups as like chloride, bromine, chlorine, bromine, and iodine. But it's important to remember that they can also be activated alcohols like a triflate or mesylate. And this will be really relevant in all the syntheses going forward. Okay. Now the important question that we need to ask is, we made one disconnection, right? We disconnected the CO bond, but this molecule is still complicated as hell, right? So it's still an open question of what is the next step in simplifying this. So there are two things that you need to start doing to make steps back. The first is you need to ask what functional groups on this molecule can you look at and say, oh, I know how to make that functional group. So this kind of anti-hydroxyamine with the O and the N are on opposite sides of the CC ring system, right? You can make those from aziridine, which is like the epoxide nitrogen analog, or from epoxide openings. So you could open this with hydroxide, or you could open this with some kind of amine, right? Now, I'm not saying that's a good decision, but I'm just using this as an example. Okay, the other possibility is So instead of having this oxygen as an alcohol, you could also consider having this oxygen as a ketone. And so you could think about it as going forward, you would start with this material where we have the oxidation state here is different, and you could do the classic reaction known as the Mannich reaction, where this amine could possibly condense onto this aldehyde here and make this make one of the cycles, and then now this this acidic CH at this position next to the amino ketone could then attack here, right? And then so then you'd have the cyclized product, but then the only difference would be the oxidation state of this oxygen. So then once you have the cyclized Mannich, then you could reduce it. Okay. So they didn't go with any of those, right? They went with a much more complicated and sexier strategy that worked out pretty well for them. So they had this interesting idea of building this, cutting these bonds and using a 3+2 cycloaddition strategy as their key step, and doing all the necessary functional group interconversion where they, change the oxidation states or change like one heteroatom to another to support that. So the first thing they do is they cut this bond. So as we know, breaking CN bonds is doable, and so they use a leaving group here. And so just convince yourself that if you rotate around this CC bond, then the stereochemistry is being correctly transferred across these two structures. And then they do something really interesting. They do something called bond scission, right? So going forward, you'd go from this molecule to this molecule. And in case you're not familiar, you can break NO bonds using hydrogenation with palladium over carbon. But then, if you think about it from a retrosynthetic angle, you want to simplify your structure with every step, right? So now this is a bicycle, now it's a monocycle with a chain. So this is technically simpler than the preceding structure. But then now you've actually complicated the structure more. So this is technically not good in retrosynthesis. But then why this is cool is you can do a paracyclic reaction like this. I don't know if that's the right word. It's not paracyclic. Whatever. It's like deals all the like chemistry, right? And so you can see here this is basically our diene, except I don't know if maybe you're not familiar with dipolar files. I forget the exact word. Dang it. Okay, someone help me with this. What is this called? Okay. Thank you. Okay. Great. So you could huh? Oh yeah. Yeah, I don't who cares? Okay. Yeah, there is an actual name for this kind of group, but you can find it in your textbook, I guess. So, you can imagine the electrons from here going into here, this alkene pushing it here, and the electrons going there, right? Okay. So you can imagine electrons moving in a ring to create this five-membered ring here, right? But then the problem here is that the polarity doesn't match, and you would get, if you assume that you get endoselectivity, you would not get this stereochemical relationship, right? So, the retrosynthesis has been okay so far, but then now they've run into a wall because they're not going to get the selectivity they want based on what they know about the chemistry. So they can do a functional group interconversion to fix this problem. So instead of an amine, instead of the cis alkene and using an amine here, you can actually start with the ester. And in case you're not familiar, there is a transformation that can take the ester and turn it into an amine. It's the Curtius rearrangement, I think. So that's an interesting mechanism. But then it's really useful here because you'll see that this one functional group this one FGI from an ester to an amine solves our problems. Now the first thing is you're going to say, okay, but you went from cis to trans, and you need the amine to be cis, you need the amine to be up, but the ester is going to be down. But then the important thing to realize is carbonyls can be epimerized, right? This center is acidic, so you can planarize it, and it'll equilibrate to the more stable epimer, right? And so that's one way that you can fix the stereochemistry issues that would arise from switching this alkene from cis to trans. And the other important thing is going from an electron donating amine to an electron withdrawing ester solves your polarity mismatch, right? So previously, this has a delta negative on it because the amine is donating into it, and this O has a negative on it. So these would not match up. These would not line up in the in 3+2. But now, because this is a delta plus, because it's conjugated with ester, and this is a minus, now these will match up, and you'll get the correct polarity lineup to get this particular arrangement. Okay, so this is kind of abstract. It's useful to see how exactly they implemented it. So as for that ester to amine functional group interconversion I had mentioned earlier, they actually do that at the very end of the synthesis, or at the beginning of the retrosynthesis, right? And so they do the Curtius rearrangement, and then they do that ether disconnection that we had previously discussed. And so now they open it to something like this. And they also oxidize this primary alcohol to the ester after, somewhere in the middle of this. So you gotta realize when you're doing retrosynthesis, things like the exact functional group you're working with can be more fluid, right? Okay, and the next thing they do is, instead of imagining this as a halogen, in their implementation of the synthesis, they had it as an activated alcohol, I think. So then they turned it back to a ketone. I don't know why. I think they protected it. It made their protecting group scheme easier. But we're just focusing on the strategy here. So now this is the cis alkene that we had previously talked about, right? So you gotta remember that when you do this NO bond cleavage, and then you turn around this CC bond to make the CN bond here, that the stereocenter flips, right? So now these are cis, so that you can epimerize at the center to make a trans. So then that's how you get this to be up, whereas this is previously down. Okay, so then moving forward from this intermediate, then you just do what we had previously discussed, where you break this CN bond, and you make this NO bond, and then now you can imagine this arising from these two precursors. Okay, so honestly, this is not my favorite synthesis of the ones. So it's because it's kind of complicated, and it's not really clear where they're moving as you're reading the synthesis. So that made it a pretty significant challenge for me as I was trying to read through it. But there are a lot of really good points about the synthesis, right? So you can see that they did a lot of functional group interconversion, such as that ester to amine. That clever switch allowed their 3+2 strategy to work, right? That 3+2 key step. So it shows how FGI can enable really creative chemistry. And then I thought that was a really interesting way to break apart that 5-5 bicycle. And the most important thing for me was they got really good yields, right? Like 10 to 15. And you'll see this is really important when we look at other syntheses down the line, because other syntheses sucked. Okay. And they had good diastereoselectivity at every step, right? So every step here, they had a reason why they would expect to get that particular diastereomer. And so they had control at every step, which is really important. Now the bad point, while it's cool that you can use FGI to enable your synthesis, it's actually technically bad to do so, because every unnecessary FGI that's not related to the actual molecule, but is just enabling you, is actually wasting a step, right? So you can think about, you could think about, is there a more concise and direct way of making this molecule? So sometimes the coolest strategy is not going to be the best one, right? Okay. But overall, it's really good. You know, they didn't have all the modern methodology that we have access to today, I guess. I don't know, it's 1986. Maybe they did. I'm not sure. But it's a great synthesis. It does what it has to do, and it's really smart with the reactions it's picked. Okay, so next I'll show you guys two other syntheses. I'm not going to go through all of them because, you know, that takes way too much time. I'm just going to focus on the key steps and discuss kind of the merits and also the bad things about what they did. Okay, so this next synthesis by the white group did a enantiomer selective synthesis of Loline. So it was not a mixture of enantiomers. And so instead of cutting this CO bond as a Tufariello group had, they cut this CO bond. And so, you know, again, we just have this and we smush it out, and then we can move forward. Now, if you imagine this X to be an activated alcohol, then you'll have a 1,2-cis hydroxyamine, right? So imagine this to be an OH. And so if we take a step back, and there is a reaction that actually synthesizes cis hydroxyamines. And it's called the Sharpless aminohydroxylation. So this smart dude named Sharpless did a lot of this kind of chemistry, right? And so you have to, the next thing that's important is this H is up. So I should have had another model here, but then because this H is up, this H is a lot smaller than the rest of this bicycle, right? So because H is smaller than this, then the reagent of the Sharpless aminohydroxylation will come from above and will not come from below. So this is what we call exo versus endo selectivity when you have bicycles like this. So this is a pretty important concept for diastereoselectivity. So they had good reason to expect that they would get this particular product out of the reaction. So continuing on with the disconnections, they do something very similar to the Tufariello group. I don't know if they had some kind of inspiration from them, but they do the same kind of CN bond cleavage. And then if you imagine that X, that leaving group, to be an activated alcohol, then we find ourselves back at this particular kind of NO bond, right? And then they do something really cool. They do a 4+2. So heteroatom deals alder. So they oxidize this hydroxyamine in situ, which is in the reaction conditions. They oxidize it, and I guess they heat it up, and then they get their desired product, right? And they know how to convert this all the way over to here. So this transformation is hydrogenation, and this transformation is activation and SN2, right? So this is really, really impressive if you think about it, because they took this structure, and it's not immediately clear how you could break this apart, right? But they rapidly just break it apart into an acyclic, just a line, which is really, I mean, it's, all right, I'm not going to keep saying it's impressive, but it's pretty impressive, right? Yeah, so there it is in words. Okay, but this had a significant problem, right? Because there's not really any control over the stereo selectivity you'd get out of this reaction. So while it's really cool on paper, ended up being a wow, that was really fast. Ended up being a pretty big problem. Okay, so let's talk about some of the good points of the synthesis, right? So it shows how modern methodologies, such as the sharpless amino hydroxylation, it completely enabled the synthesis, right? Because previously you would look at this, and it's pretty complicated to put these heteroatoms on. But then now you have a really great transformation that just does it at the snap of your fingers in one step from an alkene, right? So it's really cool that modern methodology could allow the synthesis to be so quickly simplified. Yeah, and then, sure, the other points are valid, right? But the bad point is the sharpless amino hydroxylation does not seem to be that good of a reaction in the first place. I mean, they did look out on regio control, so I gotta go back again. So the important thing to note is this alkene, the N could be put here and the O could be put here. So you could get these positions flip-flopped, right? Because there's actually no control on it, which is another reason why it's not the greatest reaction. But they did luck out. So they got a 3-to-1 ratio of the desired to undesired. So yeah, that was a dice roll in my mind, and that's pretty lucky. Yeah, and the 4+2 that I was talking about, this heteroatom Diels-Alder, was a really great idea, but it had no diastereo selectivity pretty much. So they couldn't optimize it to get what they wanted. Yeah, so unlucky overall, right? It's a great idea, but it's just unlucky. And the overall synthesis was measly. I mean, it's not feasible. This is a proof of concept synthesis, and it would not be that reasonable to try to pump material out, right? If you were a company that wanted to investigate Lolines, you would not use the white group synthesis, even though it's enantioselective. You would probably use the Tufariello group synthesis because you get 10 to 15% yield, and then you would try to separate the two enantiomers, and you get 7.5% yield, which is, that's way better than this, right? Okay. So the overall takeaways in my mind is if you don't have a plan, not having a plan is planning to fail. And it's not good to dice roll, right? Okay. The last synthesis I'll cover for now, I have one more after this, but there will be a break, is the Scheer group. So they got kind of trolled, but we'll be talking about it later. Okay, so they're the group that took the CN bond disconnection here. And so, I guess we should take a second and just convince yourself that when you smush this out, you bring this down, then you'll get this structure here, right? So they had a really creative idea, I think. So then they wanted to, there was this one particular transformation that they wanted to reach. So for now, the disconnections they picked might not make that much sense. But yeah, so they cut this CO bond here. And so they make this particular monocycle. And then if these X's, the leaving groups, are both activated alcohols, then they're going to do, see how this is cis, right? This N and this O is cis. So they're going to do a sharpless amino hydroxylation, but they're going to have a really interesting strategy for doing it. Or not strategy, an interesting tactic. And their idea is, what if we attach this functional group as a carbamate, right? So we attach a carbamate here, and based on a conformational analysis, I guess you could say, this should be above our alkene. And so if we do the oxidation of this carbamate, so you would actually oxidize this N and use it as your nitrogen in the sharpless amino hydroxylation. And so you'd get this product, except there would still be the carbonyl here, right? So you have to convince yourself that this N is going to grab onto this carbon, and this carbon is going to be hydroxylated. So you see how this N and this O end up cis, and this OH would be used as some kind of directing group. Not really a directing group, but it's going to tether the sharpless amino hydroxylation to give you the diastereo selectivity you want, right? So cool idea. Really creative. But it was actually really shit. It's really unlucky, right? So again, it demonstrates how modern methodology will allow new disconnections. And then they also had a really clever way of making this particular molecule that I don't really want to spend time going through because it takes time, but it's pretty cool to see how they do it. But they got really, really unlucky. There were just like 2 or 3 steps that just did not work out at all. And so they also had like a poor yield of like 0 to 5%. So, and the other thing that was unlucky is this synthesis was supposed to be enantioselective, but they had a lot of difficulties making that work out. So it just goes to show that doing a PhD in total synthesis can really be a dice roll. Because there's nothing wrong with this idea, right? But then it's just the molecule didn't like you, and then you don't get to publish in a nice journal anymore. But anyway, we're scientists. We're still interested in interesting ideas. So it's an interesting showcase of a new strategy. But it's still not the best overall strategy, right? So it's our turn, I guess. I hit 30 minutes pretty close. So how about we pick 1 to 3, or pick any disconnection, and try to work your way backward. You don't have to work your way all the way to the end. You don't have to worry about starting materials. But based on the transformations that you may be familiar with, it's good practice to just try picking bonds and seeing, do I know how to make something like this? So I don't know, I think I would like it if everyone could break out some pencil and paper and we could try making this together for like, I don't know, 10, 15 minutes. Yeah, it's not about making excessive progress, but it's just good practice, especially now that we've had a lot of time to look at how this molecule works. So I'll be back in like 15 minutes, right? So let's say, I'll just set a timer and we can come back together if that sounds okay. Where's my verbal confirmation, guys? I didn't see this at all. Alright, if it's too much, I can just keep going. What is this? Alright. Maybe this molecule is a bit hard. I'll just keep going. The rest of the presentation is okay. MKB is doing it. Alright. I'm gonna shut up. Okay. Okay. So the really sad thing about this is I didn't change the name. They did not ignore this part. But this is by the Trauner group, and it's really sad for the Scheer group because they published at the same time, but the Trauner group completely just dumpstered their synthesis. So I actually read the PhD thesis of the Scheer group guy. I felt like he was so cucked because like he had to mention the Trauner paper in his dissertation, but then like he didn't say anything about it. But I just felt so bad for him because he must have felt so bad about himself. Because you're gonna see that this synthesis is so badass. Okay, all right. So there's nothing special about the initial disconnection, right? But then they picked this really interesting CN bond breaking across the middle. So if you read like Corey's book about like making decisions in retrosynthesis, this is considered not strategic because this is an 8-membered ring, and I don't know if you in like intro chem class, you're gonna find that there's not that much chemistry you're gonna find at like an intro level about 8-membered ring synthesis and manipulation, right? So that's why it's previously considered not strategic. But you're gonna see that the Trauner group makes it strategic as hell, right? Okay. So then, to make make the 3-dimensional structure, right? You just need this O to tack onto this chloride, and then you invert the halogen center here, and you do this really, really cool reaction called a bromoamination. So you treat it with bromine, and the bromine activates the alkene, and then the end of this carbamate reaches across the ring, and grabs onto this carbon, right? And then this carbamate protecting group just falls off. So this is really smart because if you can make the 8-member ring, then you've greatly simplified the synthesis, right? And in case you're wondering how they knew about the stereocenter here, they actually didn't. They did the bromo amination and they saw that they got the wrong stereocenter, so they just inverted it with this reaction called a Finkelstein reaction, which is a funny name, but yeah. So synthetic chemists aren't magic magicians who can read the future. In case you're wondering about that. Okay, this is a lot. But then they converted this azide. Oh yeah, and sorry, the functional group interconversion from the azide to the amine is just a reduction of the azide with hydrogenation and palladium on carbon. So then they activate this. What they do to go from here to here, I thought was really cool, is they activate it with sockle, right, thionyl chloride. And then because this 1,2 diol, then it cyclizes it makes this cyclic structure. And the azide, if you think about which of the two are the better leaving groups, the allylic position is a better leaving group, right? And so that's exactly what happens. And you get the azide substitution there, and you get rid of this SO bond, you just hydrolyze it, I guess, and you get this product. Super clean, right? So then what they do next is they do olefin metathesis, which is a great modern reaction. Everyone should know about it. It's super useful, especially in making these larger rings. And so, just convince yourself that the stereochemistry is correct moving from here to here. And then, they simplify it really quickly. They do an epoxide opening, which is some great intro chemistry. And then they make this epoxide from this meso compound. So I'm not going to go into the exact reaction, but it's a titanium and some kind of like chiral dicarboxylic acid, I think. And so those are capable of doing, I guess you'd call it enantioselective oxidation. Super cool, super clean, super fast, super direct, right? A lot of these other syntheses that I'd gone through, if I wanted to show it all on one page, it'd be like vomit. But here, it's pretty loose and it's pretty easy to understand. The reason why I like the synthesis the most is when you look at the retrosynthesis, the intention of the retrosynthesis is clear at every step. And this is a synthesis that I'd say really illustrates the difference between synthesis as engineering. So the previous syntheses, at some point you're just putting material into reactions. Oh, it's not working? Okay, let's just go to 10 grams. Let's just make it work, right? You just gotta push material through. But, just to put more praise on the Trauner synthesis, this is a synthesis where I just feel like I can look to this and say, see, it's artistic. There's something human about the intention that you can feel about what they're doing here. Okay, that's enough bullshit like that. I just really like it. So again, we have the same point about modern methodology. You can make that point about pretty much every modern synthesis. But then they get a 36% overall yield from that epoxide. So it's not from the very beginning, but it's from a known starting material. That is crazy, right? Like 36% is like, you can make that on, you could be happy with doing that as like a commercializing it, right? I think. I'm not a process chemist, whatever. Every step is very efficient, right? So what a concession step is when you do a reaction that doesn't actually have that much to do with putting the molecule together. So the example of a concession step is this, right? So you're just turning one leaving group into another, and all you're doing is inverting the stereocenter. So if you think about it, if you could find a haloamination that gives you this stereo selectivity, then you'd be golden, right? You don't have to waste a step. But then, unfortunately, you can't get everything you want, right? So impressively, they only had 2 concession steps. I don't know if you remember the syntheses from earlier, but pretty much every other step was a concession step because they're just trying to make their stupid synthesis work, right? Okay, the bad points. No one can ever publish a total synthesis on Lolines ever again. Like that molecule is dead. Like it's already been done to the best of the ability. Okay, and like I mentioned, it feels bad for the Scheer group because they publish at the same time. Again, it's just dice roll. And so I just want to end this presentation with this quote that Barron loves to talk about. The ideal synthesis creates a complex molecule in a sequence of only construction steps involving no intermediary refunctionalizations and leading directly to the target, not only its skeleton, but also its correctly placed functionality. Okay, that's it. I hope you guys thought that was cool. Ta-da!
Very interesting. Thank you.
And you guys are pointing out my typos. Where did I have that blue lettering? Anyway.
Probably like slide 4 or 5 or some shit like that. Get it early on.
This one? Man.
It was during one of the retrosynthetic things you were showing.
Yeah, I missed a couple colors. I missed...
Keep going. Keep going.
This one?
When was that? Well, it's there. You'll recognize it when you see it.
This one?
No, I think it was earlier.
Who cares? It's a minor typo.
Just on the left. Just on the left.
No, I'm not gonna fix it.